Click on Rate. This is the second-order reaction as the rate depends on the second power of the concentration of A. To study the effect of concentration on the rate of reaction, click Next. What happens to the rate when the concentration is doubled? Answer: the rate is increased by 4 times. What happens to the rate when the concentration is quadrupled, increased by 4 times? Click on Verify to check your answer. Move the slider to get the concentration time graph. Click Half-life. Are the two half-lives the same? Answer: no. Move the slider to get the graph of rate versus concentration of A to the power 2. A straight line is passing through the origin. The graph shows that the rate is directly proportional to the square of the concentration of the reactant. Click Next. To get an expression for rate, click on Rate. Combining the two equations, we get an expression. Click Rearrange to rearrange the terms. Click Integrate for integration. Click Substitute. Move the slider to get the graph of 1 over A versus time. How do you determine the rate constant K from the graph? Click Next for the answer. Answer: the rate constant is the gradient of the straight line in the graph. What does the point Q represent? Click Next for the answer. Answer: the point Q represents 1 over A0 from which the initial concentration could be obtained. Click Next. Some examples of second-order reactions are the alkaline hydrolysis of ethyl ethanoate, the oxidation of potassium persulfate, and the bromination of ethene. Drag and drop the labels into the appropriate boxes to label the graphs. For a second-order reaction, rate equals K times concentration of A to the power 2. The integrated rate equation for a second-order reaction is 1 over AT equals K times T plus A0. The rate constant K of a second-order reaction is the gradient of the graph 1 over concentration of A versus time.